Welcome everybody to today's lecture. Today we're going to start what will essentially become a multi-part series on structures and malloc. So this lecture will cover, try to keep it in that 20 to 30 minute range, and we'll cover introduction to structures. There'll be a second lecture where we'll get a little more advanced with structures, using them with functions, and then looking at some caveats with them. Next week then we'll introduce malloc, go through quite a bit with malloc, and then use structures with malloc as well. So that's the game plan. So why don't we get started? First of all, let's take a look at what is a structure. So we've had, up until this point, we've worked with essentially two data types, that is primitives and aggregates. The only aggregate that we've worked with has been an array. Primitives are something simple, like an int variable or a char variable or a double variable. It's a variable that points to one single value. The arrays then, being an aggregate, it allows us to aggregate values together. With arrays though, we type the array, so we say that our array is of type integer or double or char, whatever the type is, and all items that are stored in that array are related by at least the simple fact that they're the same data type. So aggregates, arrays, they allow us to aggregate data together. A structure then is an aggregate data type that stores related data items of different data types under one name. Okay, so with a structure, we can define it. We'll define the members of the structure, and I'll show you those here in just a few minutes. And they can be a combination, really any combination you want. It can be another aggregate, such as an array, or another structure, and they can be primitives, or any combination thereof. With structures then, this really, at least in my mind, gets us one step closer to more object-oriented patterns. That is that with a structure, we'll oftentimes define a structure to mimic some sort of a record or file format or data format that we're looking at. An example that comes to my mind is a tweet, right, on Twitter. We could create a structure that has members that mimic a tweet. So some of those members would be the user that posted or that tweeted, the content, the time, maybe information about that tweet, the number of times it's been retweeted, whatever it is. You know, that information for Twitter is probably going to be stored in a database somewhere, but if we wanted to load that up into a program, then we could use a structure in that program to represent that data. Pull that data out of the database, put it in the structure, and now we have a variable to use in our program that lends itself very well to that data format, that data structure that we want to create. Here you can see, we'll talk about the definition, so the actual structure of a structure. All right, derived data type. Structures are a derived data type, and that means that a structure, a struct, in and of itself, doesn't really make any sense, right? If I just said struct card in this example here, but I didn't define any members, let's say that we didn't have any of these members, then the structure, the struct card wouldn't make any sense. Where the derived data type gets its purpose is from the type of members that we define. The members themselves are what make the structure useful and have meaning. Why isn't my eraser? There we go. Okay, so when we look at a structure and how we define it, there's some key pieces here. First of all, we have to use the struct keyword. Okay, then we have the next portion, which is, this is considered the identifier. Okay, struct is a significant keyword in C. We have to use that. We have to tell the compiler that we're about to define a structure. The second piece then, the identifier tag, this is whatever we want to call this structure. All right, so in this case we have struct card. Card is what I'm using to refer to this structure. Then we have curly brackets. This bottom curly bracket ends with a semicolon, so don't forget that. And then in between we have the members. Okay, so this structure is struct card, and it has two members. These two members are char pointers. Okay, so refresher on strings. Keep in mind, we've talked about two ways we can define a string in C. One is a pointer. Okay, as we see here, char, it's a char pointer. So we use the char type, and then we use the asterisk character to define it as a pointer. The other would be a char array, which is not what we did here. There are some challenges that we'll run across when we use members in a structure based off whether we're using a char array or a char pointer, and we'll cover those when we look at the code here in a little bit. So when you look at the components here, okay, we talked about struct, We need that as a keyword in order to tell the compiler we're about to define a structure. We have the identifier tag, okay, and that's the card, so whatever we want to call that structure. And then we have the members themselves. As far as the members go, okay, as you can see here, they must have a unique name within the structure. Okay, they can overlap with other variable names in your program, but within the structure itself, so basically anything in between this curly bracket and this curly bracket, those have to be, these member names have to be unique. All right, when it comes to defining the members itself, okay, here you can see there's another example, an employee. Okay, card, employee, employees make another, that's a good data type. There's a lot of systems that you're going to interact with in your career that are going to be based off of you as an employee, whether it's a time clock program, you log in to log your time, or maybe you're running pen tests and you're logging in to run the test and produce the audit results. Either way, you're going to be represented in a program, and so structures represent employees really well. Because if we needed to store that information about me or you as an employee, we'll probably have things like a name, first name, a last name, an age, a gender, a salary, an access level, a role, whatever you think of whenever you think of when you need to define the employees within an organization. So here's another example then, looking at the employee. So here we have the struct keyword. We have the identifier tag, which in this case I've called it employee. We have our opening and closing curly brackets as well as a semicolon, and then we have the members. The purpose of this slide is just to tell you, well, one, here we have our char arrays, okay, so the second way of identifying a string, and then we also can have different data types, right? So here's a couple of aggregates. My horrible penmanship on this. A couple of aggregates, and then here is a series of primitives. It doesn't matter. The structure, you can define any combination. The only thing we have to be worried about is that these names are all unique within the members themselves for this particular structure. Okay. There is one catch though. Okay, so outside of making sure that the names are unique, if you define a member that is of a structure type, it cannot point to itself. Okay, so this is an example of that. We shouldn't necessarily run into this, but just be aware of it. If you try to define a member that's a structure of the same type, you cannot do this line of code right here. Okay, you can do this. Okay, so this would be a pointer to struct employee. This bottom one right here. This top one is a variable of struct employee, and this is something you cannot do. Why would you want to do something like this? Well, in this example, using an employee structure, it would make sense that I might have, okay, maybe a better name here would be supervisor. Right? Oftentimes in an organization, unless you get to the very top, there's going to be a hierarchical relationship. And so me as an employee, me as an instructor at Dakota State University, I have a boss. He's the dean of the Business and Information Systems College. And so this would help then if I have have to display or show the relationships in my data. I could have a member that's of type struct employee that points to another struct employee, and then that employee could contain information for my boss. So it happens. This will be a very common thing, but we won't necessarily be doing this in the lab. So just be aware that if you do define a struct, a struct that has a member that is another structure and it points to itself. Okay, that's the other big thing here, is these are members that are pointing to the same type here. That if you do that, it has to be a pointer. It can't be just a straight variable. All right, let me get rid of that. Hopefully that makes sense. As you can see here, that is an error. So if you go to compile this code, I don't know offhand, I don't recall offhand what the error will be, but if you try to use this here, you generate a compile error. Okay, well, an error or a warning, I'm not sure, but something will come. And we talked in the last lecture about errors and warnings. while when you compile your program and you get a warning, you still get a compiled program. You can still run it. It's still best practice to not ignore the warnings. You still want to go and look at your code and figure out, why did I get a warning and how do I fix this? Okay, so we're getting to know a little bit more about structures. We should have at least a basic understanding or a kind of a general idea of how we would define them and what we would use them for. How do we declare them? Okay, just like anything else we've done in C so far, we'll declare them as a variable. We just give them a different type, a different data type, an aggregate data type, a derived data type. So the sample code here, you can see that we're using the struct keyword again, struct keyword, and then the identifier tag. So in the very first code sample that we looked at, that very first screen capture, I declared a struct card. Okay, so here I'm saying that the following variables are going to be of type struct card. Okay, and then I go and I define 3 variables. Okay, this one, a card, is just a regular variable. This is a deck with 52 elements. So this would be an array with 52 elements, and the elements would be of type struct card. And this last one then would be a pointer. Okay, so they're no different than anything else we've used, except that they're pointing to an aggregate type, struct card, whatever the structure is that we want them defined to. All right, so keep in mind then, as we go through the sample code, what we'll look at here is we'll look at defining it as a variable of struct card and a pointer that points to a struct card. And we won't really do a whole lot with arrays, okay? But it's still important to understand that this is the syntax for doing it. So just be able to understand that. All right, limitations. There's some things we can and can't do with structures. Let's see here. Let's see, so we can assign structure variables to structure variables of the same type. Yeah, we can do that, and you don't have to worry about that one too much, but you can say, you can declare a structure variable and then another structure variable and assign one to the other. And I don't have a code sample there, so that's not something you need to really worry about. You can get the address of a structure variable, and what this means is that we would use the address operator, right? So we've been working with pointers, and what this allows us to do is once we define a structure as just a simple variable, not a pointer, we can use the address operator on that variable and assign it to a pointer. Okay, and we'll need to do that in order to use pointers. We can access the members of a structure variable. Of course we can do that. If we couldn't, what would be the point of defining a structure? When we get into malloc, okay, the size of operator is something that we'll use a lot more. And we'll use that to determine the size of a structure variable. And so just to give you a little bit of a, I guess, a glimpse into malloc, malloc allows us to dynamically allocate memory as our program runs. This makes our programs more efficient because we can allocate the memory when we need it, we can deallocate it when we're done with it, and that just frees it up. So when we do that, when we request memory from the system, we need to know how much memory. The system needs to know how much memory we need, and we typically will do this in bytes. And so the size of operator will allow us to say, you know, hey operating system, I need 24 bytes of memory. All right, so this size of just helps us determine how much memory we actually need, and we'll use it quite a bit next week when we get into malloc. The last thing you cannot do, and that is you cannot compare structures together. Right? I can't declare 2 structure variables, you know, struct1 and struct2, or you know, a card 1 and a card 2. I cannot compare them together. All right, you can't use equals equals, and you can't use exclamation equals or not equals. You can compare the members, okay, because the members are just going to be primitive or aggregates. If it's an aggregate, it's an array. You still have to compare the individual element, but you can't compare the structures themselves. You won't get a valid condition. Okay, so we've talked through some caveats. We've talked about what the kind of the structure of the structure, how we declare them. Now we need to figure out how we initialize them. How do we actually get information into the structure itself? The first thing we can do is we can use initialization lists, just like we did with arrays. Okay, so here's an example. We have to use struct and the identifier tag. That's telling the compiler that this variable right here, this variable that follows, will be of type struct card. Now we have a single equal sign, so this is an assignment operation. What follows on the right-hand side then is an initialization list. Recall with arrays, when we use initialization lists in the arrays, we use these the curly brackets, the opening and closing curly brackets. Then what came in between those was our initialization list. We had individual initializers. The list it can be no greater than the number of members that we have, but typically you're going to have the number of members that you want to initialize the variable to. Okay, so what does that mean? Card had 2 members, right? Face, face, we can look down here to cheat. Face and suit. Okay, so 2 members. So if I want to define this variable with values in each member, then I need to provide 2 values in this initialization list. All right, we define these just like an array. When we provide an initialization list to an array, the initialization list values get assigned in order. That means that the first one goes to element 0, the second one goes to element 1, or index 0, index 1, element 2. Same with this, okay? The first member, the second member, third, fourth, and so on, however members we have. We can't define a third initialization value because there isn't a third member. So that would generate, I don't know what it generates, a warning or an error. We can define less than. Okay, so our card structure has 2 members. We could only define 1, and it just means that face would get a value, but suit would not. Actually, let me just back up 1 second here. All right. Okay, yeah, you can see the second bullet here. Less values than the number of members will assign a default value of 0 or null. All right, the other thing you can do is that once you've declared a structure, a variable type of structure, you can assign values to the members directly. Okay, so this right here is an example of doing that. You can, once you access those members, you can treat those like a variable of that type. Okay, we know that face and suit are char pointers. We know from our work on strings that when we have a char pointer, we can just assign it a value surrounded by double quotes, and that's what we're doing here. Now, there's one thing you'll have to notice, and we're going to talk about these in the next few slides, is that dot. Okay, we have the dot operator and the arrow operator, and we'll talk about how do we access the members of a structure. Okay, so dot operator. That's what's first, and you've already seen that. Get rid of that, was kind of a... All right, dot operator. So this is the dot operator. Obviously, it's just a dot. We use the dot. So we have the variable name of our structure variable, and then dot, and then the name of the member. All right, so that'll access that member, and that treats that as basically as an instance of a variable of that type. Okay, so we know that face was a char pointer, so if we use our format specifier to print a string, that'll print a string. And we could run that code, and you'd see that it would print whatever value we had stored in that member on that structure. All right, we use the dot operator when we have variables of that structure type, not pointers. Okay, so these are just for variables. The next one is called the arrow operator. Okay, so there's 2 ways we'll access those members, the dot operator and the arrow operator. We use the arrow operator when we use a pointer. Okay, so here's an example of that. Here we have struct card. Okay, so remember, if we're going to declare a variable or a pointer of a structure type, we have to use the struct keyword and then the identifier tag of the structure that we want to create. In this case, now we have 2 variables, right? We have a card and a pointer. Right, so this is a variable of that type, and then this will be a pointer of that type. With this, okay, if it makes it easy, it's with non-pointers, you use the dot operator. All right, so we have a card, we didn't initialize it to anything. We can access those members, face and suite, using the dot operator because it's not a pointer. And we can say that dot face and dot suite equals face and equals hearts. Right? Well, with a pointer needs to point to a struct card. So in this case, we can point it to a card. So if I say that a pointer equals, and this is where we talked about earlier, we can use the address operator and then that variable name. Right? So we can get the address of this variable right here and assign it to our pointer. And now if we want to access those members through a pointer, we use the arrow operator. that's just a dash with a greater than sign, right? So arrow operator, we use those with pointers. Dot operators, we use those with these variables, so non-pointers. All right, the other thing I want to point out, we're going to look at this in the code, but I want to say it a couple times because it'll catch you off guard if you're not paying attention. So let me get rid of these red marks here. This right here, okay, we're using the dot operator, and these are char pointers. Okay, so this assignment operation works just fine. If these were char arrays, this would not work. You get a syntax error, and I'm going to cover that in the code samples today. So just keep that in mind as you're starting to work with structures, as you work with structures for the next lab. If you run into this, this only works with char pointers, does not work with char arrays. And hopefully once we go through it in the code, it'll make complete sense. But I just want to really stress that. So that's it. Let's see here. For the next slide, we got structs and functions. All right, so we're going to cover that in the next lecture. So we're just going to look at sample code from here out. Again, we can, so to kind of wrap up what we talked about how we define a structure. Okay, so we have to use the struct keyword and then the identifier tag. So what we want to call that structure. We have our opening and closing curly brackets. The closing curly bracket has a semicolon that comes after it. And then in between those curly brackets, we define our members. Those members can be primitives. Those members can be aggregates. Those members can be other structures. They can be a member to the structure itself. It can be any combination as long as the names are unique and one of the members doesn't, if it points to itself or a type of itself, it has to be a pointer and not just a variable. Just like our functions, if you want to use a structure in main, you have to define it before main. The compiler has to know about it. If you define it after main, then you're not going to be able to use it in main. Okay, so you have to define it above main so that when you compile your code and actually use that structure in main or in another function, it's already defined. The compiler can find it. You can't define it in main as well. And so you'll see that here in the sample code in just a second. Let's see. I think that's all I can think about for right now. So let's take a look at the code. Go ahead and discard those. All right, so there's quite a bit in this file right now, and we're going to use this for both this lecture and the one that follows. I'm not going to comment it out just because it'll generate a whole bunch of errors, and I'll probably end up confusing myself and then you in the process. But I will hopefully just highlight and talk through, so hopefully there isn't any issues with this. To begin with, let's take a look at the includes. Just don't forget standard IO, standard lib, and then I'm including string.h because we are using strings here. The next thing I want to look at is this structure, and I was playing around with this one and I made some changes, so I want to make sure that I change this back to what we saw in the code sample there in the slides. All right, so this is how we define a structure. You can see that I've done it before main, and I've also done it before any of my function prototypes, and we'll take a look at those function prototypes in the next lecture. Prototypes, there we go. All right, so here's the struct keyword. Here's our identifier tag. You can see there's the opening and closing curly bracket, plus it ends with a semicolon. On top of that, then, we just define our members. Okay, we can define them how we define. This is just like declaring a variable. A couple of things, important things to note here. One, we have each one's going to end with a semicolon, and we don't initialize them to any values. I don't say this is equal to 0 or null or anything. Okay, you don't do an initialization. Okay, there's no assignment operations done inside the structure. We're just defining the name of the member. Okay, the name of the member and then its type. All right, so in this case, these are both char pointers. All right, I'm going to do one thing quick, and you'll see here I've got quite a few printfs, and I'm just going to get rid of some of these printfs, at least for now, so that as we run this program, there isn't a whole bunch of output to the terminal. All right, that takes care of that. Okay, so first thing we do, how do we declare a struct? Well, struct card. Okay, I use the struct keyword, and then the identifier tag from the structure that I want to declare, and then the name of my variable. All right, so there's struct card, and I'm calling this a card. In this case, I'm using an initialization list, and I'm providing two values. My structure for card has two members. They're both char pointers, so I know that I can use double quotes and provide two values, so king and spades. The next thing I'll do is we'll print those members off. So they're both strings, so I can use the format specifier for a string. And because this is not a pointer, we use the dot operator. So a card.face and a card.suite, or suit, however you like to pronounce it. Okay. Keep in mind, I'm on a Windows machine. I'm using Cygwin, and so this is going to be compiled. It's going to use GCC, but it's going to run in Windows still. So my out it's a.exe instead of a.out. It's exactly the same, except you're going to see me type in a.exe instead of a.out. Okay, so please don't let that confuse you as well. Structures.intro. Okay, and here we go. And there you see, there's the print off. Okay, one, the code compiled, there was no errors, there was no warnings. And two, it printed off both of those members, king and spades. Okay, let's say that I did this, and I didn't use that initialization list, and I want to assign a value to that structure. Well, now I can say a card dot, okay, this is not a pointer, so we use the dot operator. So a card dot face equals, and I'll just say face, and a card dot suit equals, and I'll say suit. Okay, so we'll save that and compile it, run it again, and there you see face and suit. Okay, so whatever the members are, you can use when it's not a pointer. You use the dot operator, the name of the member, and then you assign it a value accordingly. You're just essentially using a variable of that type. Okay, same with format specifier. If you want to use the value, use the dot operator and the name of that member. Okay. I'm going to rewind this just so when I haven't uploaded this to D2L, so when I get it out there, you guys have exactly what we were looking at. All right, let's look at another structure, Struct Employee. And you can see here that I have three structures overall. We've looked at one, now we'll look at the second one. There's really nothing different here, other than I'm using members of different types, and I'm using quite a few of them. Okay, so we have another char pointer for first name, another char pointer for last name, an int for age, a char for gender, and a double for salary. Right? So all of these are just primitive types. And there's no restrictions on them being different data types. Two chars, an int, another char, but this is just a single char and then a double. It doesn't matter, as long as these are all the same. You'll also notice that we do not initialize any. I don't set any to 0. You don't have to do that when you have your structures. All right, this next little bit of code then, this talks about declaring a structure employee. Okay, I called mine a employee, and then assigning values to those members. Now, once we've declared a employee, because this is not a pointer, we can use the dot operator, access each individual member, and assign a value to it accordingly. Okay, so first name and last name, those are both char pointers. So here you can see I can assign a first name and last name. Age was an int. Okay, so you can see I've assigned an int. Gender is a char. I can assign a char. And salary was a double, so I can assign it a double. And then, just like we did in this previous example here on line 37, we could print off each individual member. We could pass members as as an argument to a function. It doesn't matter. When you access a member, you're just accessing a variable of that type. With this one, if you wanted to, you could also provide an initialization list. Okay, so we just have to go in order. First name's a char pointer, last name's a char pointer, then we have age, then we have gender, and then we have salary. Right? So if we wanted to do that, we could do this using an initialization list instead of this. Okay, they just need to be provided in the same order that we define the members. Okay, so in this structure here, struct employee, I define the member as first name, last name, age, gender, salary. So when I provide those in an initialization list, I have to provide them in that order. first name, last name, age, gender, and salary. Okay, that's what it's expecting. That's the order that it's expecting. Okay, so you could do either one. If you did this, use an initialization list, then of course you wouldn't have to use this. But after you've declared this variable, anytime after that in your program you want to change the value, you can use dot notation, dot operator to access that member and change its value. Okay, and I don't print any of those right now, so we'll look at a function here in the next lecture, and you could go back and print them if you want, but you don't need to. So the second, here, let's look at a second structure, excuse me, employee 2. All right, and I declared a second one really to give us an opportunity to talk about the difference between a char array and a char pointer. Okay, I talked about it earlier, and now I want to show you why there is an issue. So look at Struct Employee 2. It's exactly the same, except that first name and last name are char arrays. They're not char pointers. When you declare these members as arrays, you have to do exactly how you would do it if you were declaring it as an array outside of a structure. Okay, if I was going to declare a char array for first name, I would need to first declare it as a char, of course, but then also define the size. Okay, so that's the big thing here, is that you do need to define the size inside the structure when you define that member. So that's the only difference. Employee, those are 2 char pointers. Employee 2, those are 2 char arrays. So let's take a look at this code. So up until this point, everything's been compiling, right? No errors and no warnings. The one modification I'm going to make is I'm going to get rid of that printf. We don't need to see that one anymore. What if I comment these out? All right, so a employee 2, we declared a employee 2 right here. This is not a pointer. Okay, so using dot notation, or the dot operator, that's fine. That's what we have to use. So a employee 2 dot first name and dot last name, and I'm assigning it a string value. Do you think that works? Well, obviously, if you're looking at the code, you can see it doesn't. Let's see what happens. Okay, so we get errors, right? Errors are bad because that means the code did not compile, and I do not have any sort of executable or binary that I can run. So I've got to fix an error. What does it say? Incompatible types when assigning to type char array 30 from type char pointer. Okay, so what does that mean? Well, that means that as far as the compiler can tell, you're trying to assign a string, so a char pointer, to a char array. We can't assign this to a char array. Okay, this is an array, and if you were doing this with a normal array, you'd have to use a function. You'll see there at the bottom 61 and 62 string copy. What is the value of an array? Just the value of a variable that is an array, first name and last name. Well, let's comment that out so our code will compile. And let's take a look. Okay, so it's a memory address, right? When we looked at using arrays as functions and we started working with pointers, some noticed that when you declared as one of the function arguments, maybe an int pointer, and you were expecting an array, and then in your code that called that function, you just passed it the value of an array variable, it worked. You didn't get any errors, and it actually worked exactly as you expected. Well, that is the case. Arrays are essentially pointers, and that the value of an array variable is a memory address. So what do I mean by that? I mean, first name for that structure we know is a char array. It's an array. If we want to access the individual elements of an array, we have to provide it with an index. Okay, we have to use the square brackets and then provide it with some sort of an index. But when we just access the array itself, that actually is essentially a pointer. It has the memory address that points to those blocks in memory. Okay, remember, arrays get assigned a contiguous block of memory, and when we start using the size of operator, we'll see that it's a contiguous block of memory based off of the size of the data that it's going to hold. But it's a continuous block of memory, and this is just the memory address to that very first block. So if we run this code, and you'll see when we print off the value of first name, the value of that array, I'm using the format specifier %p, and you'll see that it prints off a memory address. Okay, so that compiles right, no errors, no warnings, and we'll clear it and then we'll run, and there it is, right? There's the value. It's a memory address. So if you start to think of this now as a pointer, why doesn't this work? Well, if this is a pointer, what's the value of a pointer? The value of a pointer is a memory address. This is most certainly not a memory address. So that's why you get the incompatible type. That's why it says you're trying to assign to a char pointer something that is, this is actually a char array. And that's why it doesn't work. Okay, so how do you fix that? Well, we can get rid of this now. We have to use string copy. strcpy. And what that does is it says, well, here, let's go take a look at it. So if I ever come across a function, I'm not really sure what it does. I like a site called tutorials point, and I'll call, so this is what I normally do. Tutorials point, string copy. You can see I've already visited this site before. And here we go. Now we can take a look at what is it? Well, it returns a char pointer, and it expects as two arguments char pointers, right? So char pointer destination, char pointer source. So this is where we want it to go. This is the value. This is where it's coming from. So we're saying we'll copy from the source to the destination using two char pointers. This is constant. Okay, you can use that keyword in any of your code, and what that says is that I will not, constant means that inside this function, so inside string copy, this right here cannot be changed. All right, it's constant. Constant means you cannot change it. It's like read only. So if we go back and look, then we can see using string copy, what I wanted to do, okay, we'll just look at first name. I wanted to copy my name into the first name member. Well, if we use string copy, we can copy. This is what I want to copy, and this is where I want to copy it. Right? So it's really simple. It's another layer. It's another thing you got to remember, but it's really simple. Okay. This is only when you're using char arrays. Okay, and you might have an occasion in your structures where you need to use a char array instead of a char pointer. Remember, the difference is that with a char pointer, those are typically read-only. You typically can't iterate over them. So if you need to access the individual elements, the individual characters, change them, modify them, you can't do that with char pointers. You're going to need a char array. So it all depends on what you need.